And this one, okay, this moment you don't need to understand, but naming. This form is often right in this way. This is a definition of the form. Again, this means this is FF here. And this is called Poisson bracket. Poisson bracket. So, therefore, when we talk about the dynamics, there is two views. One, using Poisson bracket, we write Liouville equation. Another is you write Hamilton equation of motion, and then you ask the evolution of the function, the trajectory. Now, both are fundamental, especially when you go to the quantum mechanics. In quantum mechanics, you have a wave function, and you follow the evolution of the wave function. That is a Schrödinger equation. Okay? What did this mean? Look, quantum mechanics ask the evolution of function. Okay? It's not evolution of point, quantum mechanics. Therefore, this formulation in classical mechanics is much closer to the quantum mechanics, a Schrödinger equation. Actually, that evolution is a more Heisenberg equation of motion. You see, in the quantum mechanics, there is a two set of the fundamental law, Heisenberg's matrix dynamics. And it's called the Heisenberg equation of motion. And there is another formulation, is a Schrödinger equation. And you have a wave equation. And actually, that two method is a complement. Classically, there is such structure. Point that Heisenberg picture. Here is a Schrödinger picture. And almost all cases in quantum mechanics, people are talking about the Schrödinger equation. You see, on the other hand, when you learn the classical mechanics, often you never go to Poisson bracket, isn't it? Always you are talking one. And that is quite unbalanced. You have to understand both. Otherwise, you don't understand the quantum mechanics. Now, in 10 more minutes? 5 minutes. 5 minutes, okay. Now, then I will close today's talk. So you already learned many important concepts today. Hamilton equation of motion, canonical variable. Phase, canonical variable means if it satisfies Hamilton equation, this set is called canonical pair. You see, canonical pair satisfies these two equations. So this is a canonical variables. And then from one canonical transformation to go to the another canonical variable. From one canonical set to another set is called canonical transformation. And by a very clever method, often you try to make, by the canonical transformation, it's make cyclic. If you can find it, you can find the invariant of motion, and through the invariant of motion, you can solve the equation of motion. So that is one very important root. No matter how complicated you will do in physics, that is always the root. See? And then another view, that is a point transformation, but there is another view, it goes to the function transformation. And now, no, I will not go because I have no time. So, anyway, let's go back again. This, I will talk the next time here. But here, I will tell this one story. That is an announcement of the next talk. You see, this shows, suppose you have n degrees of freedom. Here is a 3n. If you can find 3n invariant of motion, you can solve it. Actually, more 3n independent invariant of motion. But suppose you have a 3n degrees of freedom, then you have fewer the invariant of motion. By chance, you could find 5 or 6, not enough. That case, you cannot solve the problem. Therefore, to find the solution through the integration, you have to find the same number of the invariant of motion of the degrees of freedom. So that means in three-dimensional case, one particle three-dimensional case, this is 3 degrees of freedom. Therefore, if you can find 3 independent invariant of motion, you can solve it. But if it's 2, you cannot solve it. If it's 1, more of course cannot solve it. And now point is therefore, after the Newtons solved the 2-body problem, people try to solve the 3-body problem, and the 3-body problem is how many degrees of freedom? In each particle, you have a 3 dimension. Therefore, 3 degrees of freedom, but there's 3, therefore 9 degrees of freedom. Now, but the center of mass is simple. But center of mass move in the 3 dimension. That means you have 3 coordinate is already solved. So that 9 minus 3 is 6. So this is a 6 degrees of freedom. Now, therefore, you have to find a 6 independent invariant of motion using this transformation. Then you can solve it. And many, many geniuses try to solve it. And Gauss, Lagrange, Euler, you can name it. All great mathematicians tried to solve it. Nobody solved it. Could not solve it. 200 years. More than 200 years, 3-body problem. Nobody could find 6 independent degrees of freedom. Independent invariant of motion. You see, then I will tell you that the next time, Poincaré, 100 years ago, actually he showed that there is such system that the number of invariant of motion is less than the number of the degrees of freedom exist. In another word, 3-body example is a 3-body problem. 3-body problem, in principle, you cannot find 6 independent invariant of motion. What did this mean? By any canonical transformation, you cannot solve the equation of motion, in principle. And that was a very big surprise, because everybody assumed that when you write the equation of motion, eventually you can solve it. But the Poincaré showed that there is such system, you can never find enough number of invariant of motion. And that is a discovery of chaos. Modern day, everybody are talking chaotic dynamics, chaos. That is actually coming from this Poincaré's discovery. And therefore, next time that I shall show you that why in principle you cannot solve the dynamics. Thank you very much.